this learning object, we'll be working on question 81 in section 1413, dealing with standing waves on strings. So let's read the question. A string.
No, I disagree because the filling, it depends on what you're eating, right? If it's... Whoa. But it's just a thread.
Of length 100 centimeters.
Like this.
Is fixed at both ends.
Fixed.
And is kept under a tension of 25 newtons. The linear mass density
Sorry, what?
of the string is 0.65 grams per meter. And given this information, we are asked to solve 4 questions. So let's tackle these questions.
Kaepernick. Underneath, he's got Vernon Davis who gets popped. Ball is out, and now they're going to say no catch.
First off, let's write down what we know. The length of 100 centimeters, which is 1 meter. The tension force of 25 newtons. And a linear mass density of 0.65 grams per meter, or 6.5 times 10 to the negative 4 kilograms per meter, to put it in correct units. The first question is asking what the lowest resonant frequency is of the string. I initially wondered what that was.
Then I got to thinking.
That's the fundamental frequency.
Oh, look! The pencil's rubber!
Also known as the first harmonic. And to calculate the frequency of the first harmonic, the equation is 1452 on page 412 of your textbook. It states that the frequency for the first harmonic is equal to 1 over 2L times the square root of T over mu. This equation works well because L is length, which we have, T is tension, which we have, and mu, which is the linear mass density. And we have all of these values. So if we just plug it in, 1 over 2 times length of 1 meter times the square root of 25 newtons over 6.5 times 10 to the negative 4, which is our linear mass density. And this gives us the fundamental frequency of 98.06 hertz.
Sweet!
The second question is asking for the frequency of the second
That's 2.
and third
That's 3!
harmonics. For this, we need a more general formula for calculating frequency. This would be equation 1451, also found on page 412. It states that the frequency of a given harmonic is the number of the harmonic divided by 2L times the square root of T over mu. So for the second harmonic, we do 2 divided by 2 times the length of 1 times the square root of 25 newtons over 6.5 times 10 to the negative 4 kilograms per meter. And that gives us a frequency of 196.12 hertz. For the third harmonic, we do 3 divided by 2 times the length of 1 times the square root of tension 25 over the linear mass density of 6.5 times 10 to the negative 4. This gives us the frequency for the third harmonic as 294.17 hertz. Now the third question is asking for the speed.
Good news, guys. I spent all my money.
Boy, you can't bring that in here.
Yes, I can. It's all terrain, dummy.
Of the wave for this string. Now this is a pretty simple question because we know that velocity is equal to the square root of tension divided by linear mass density. Since we have both the tension and linear mass density, we can simply plug and play. So velocity is equal to the square root of 25 over 6.5 times 10 to the negative 4. And so the wave speed is equal to 196.12 meters per second. For the last question, it's asking what is the lowest resonant frequency when the tension is increased to 35 newtons. As we saw earlier, the lowest frequency is the fundamental frequency. So does that mean we can use the same equation as before?
Can we? Yeah, you can. All right. We can, we will. I just wanted to make sure. We will.
Okay, good. So frequency is equal to 1 over 2L square root T over mu. Now we use the same L, the same mu, and the new T of 35 newtons. Plugging that in, that becomes 1 over 2 times length of 1, because it hasn't changed, times the square root of 35, our new tension, divided by the same linear mass density of 6.5 times 10 to the negative 4, and that gives us a new frequency of 116.02 Hertz. And there you have it, standing waves on strings.
What? That was awesome!
We were caught up and lost in all of our vices. In your pose as the dust settles around us, and the walls kept tumbling down in the city that we love. Gray clouds roll over the hills, bringing darkness from above. But if you close your eyes, does it almost feel like nothing changed at all? And if you close your eyes, does it almost feel like you've been here before? 'Cause it's too cold for you here and now. So let me hold both your hands in the holes of my sweater.